Good afternoon. Good afternoon. Welcome. I'm so glad to see you all here. Kind of a week before the last week of semester. It's almost kind of hold your breath. It's almost done. I know a lot still is left to be done. So today we have 4 presentations. 2 people, Mckenzie, Larson, and Marty McFadden. They're going to talk about their internship and their experience. And then Ryan Calez and also Marty one more time are going to present their research work. So we start with Mckenzie Larson. I really appreciate it at a short notice. You're coming up here. Please go ahead.
Okay. So I guess I'll just talk a little bit about how I got started my internship, and then open it up for any questions. Just ask me anything. So this summer, and partly into the semester, I interned at a place called Lam Research. And Lam Research is known for making manufacturing and servicing semiconductor processing equipment to be used in the fabrication of integrated circuits. So I worked with their IT department over the summer. Really how I came across this internship was through networking. Good family friend of mine knew that I was computer science, asked what year I was, said that I was a junior transitioning to senior over the summertime, and said, hey, Lam hires about 75 interns over the summertime. You should give it a shot. Just put my name in, sent me the application. And I was already looking through, seeing what other opportunities were available at different companies. But I took a look at Lam online, thought, hey, that might be pretty cool. I've never worked at a company like that before, ever. This is my first internship. So I interviewed, and knowing people there really helps. I ended up actually knowing a couple people from my hometown who worked at the company. So mentioning their names, talking to them a little bit more, researching about the interview process before I went in really helped me out. So then got the internship, started there. It was a full-time internship over the summertime. I was working 40 hours a week, and I had my own cubicle, which was really nice. And I was helping the company with transitioning from a thing called SharePoint, an older version, to a more updated version. So I was working with a technical team and a non-technical team. So I was able to learn the technical side behind how they were able to upgrade. They have 8,000 employees worldwide, so how they were able to upgrade all of these people without messing any of their information up, because SharePoint is basically like Google Drive, but for companies that have trade restrictions, so you're able to control the documents that are being uploaded online, who can see them and who can't. So we needed to upgrade all of these sites within SharePoint and all these documents without messing anything up. So I was able to see the technical side, but management also had me floating around and working with other groups as well. So I was working with a management team for a little bit, technical team, and a teaching team. So I was creating, I had to learn what SharePoint was, so I feel like I'm pretty expert in that now. And I had to create training materials and teach classes, but then I was also working on back-end stuff and working on the websites for them. Some highlights of my internship, really, other than actually working, where the interns, we all got together and we went on a trip. Instead of working for a day, we went up to San Francisco. So I was able to network with other students who were either graduate students or undergrad students. Was able to swap some contact information and just have a fun day in the city. We had an intern brunch with the CEO of the company, so I was able to shake his hand and introduce myself, which was really cool. Just again, more networking is really what internships are about. At the end of the summertime, before everyone went back off to school, we had an intern fair, so we were able to go around, because there were about 70-ish of us at the fair that day, and we made presentations exhibiting what we did that summer. So we could just see, because there's so many different departments, so we were able to see what other students were working on. So while I was in IT, someone was in R&D working on something that would image through a chip and see the colors and make sure that the chip was working properly. So that was pretty cool. At the end of the summertime, this helped really with talking to people. I had to make a presentation and present it to the CIO of the company, which in front of all of his, he had like a little board in there as well of like 10 people. So I got to stand up, present for about 15 minutes what I worked on, my contributions, and give feedback about the intern program. And then really my final thoughts on my internship and just my experience overall was that Lamb Research, what I found was that the company itself really cares about its employees. There are all these benefits about how they have this mantra about, you know, your health comes first, your sanity comes first, you know, we don't want to work you to the bone. It was really, you know, their core values were being instilled in their employees every day. And while there might have been a solution that might have been better for the company, it might have been cheaper for the company, the one that would benefit the customer and the employees would come first over that. So I think really when you're researching a company to work for or intern for, make sure your values match with their values. So read employee reviews on Glassdoor, really see, I guess, what's the word? How really their values fit with yours, because that'll make you happy. I was proud working for them over the summertime. I wasn't working going, you know, they don't really fit with me. I felt like we had a good fit. It was definitely something new and different that I've never tried before, and it opens up opportunities in the future. So definitely recommend internships if you can. Talk to people that you know, talk to your professors, work your connections. Really about it. Any questions?
Any questions for Mckenzie?
Yeah.
What kind of programming did you do?
I was doing some JavaScripting. They taught me PowerShell scripting as well over the summertime. It was kind of really depended on the project that I was working on. I was working with something called Splunk too, which analyzes machine data. And I was doing some JavaScripting for that. So it's just kind of like working with what you have. Like I would do some C++ here and there on really whatever project they wanted. So it was like every other week I'd be doing something different. Yeah.
You said something about something called Glassdoor. What is that?
Yeah. So Glassdoor is a website that has company reviews, helps find jobs and stuff. So you can like search on it, like salaries of a company, employee reviews of a company. They also have, if you're preparing to go in for an interview, they have like old interview questions that interviewees have posted online. So say like there's a coding problem that they might potentially give you during an interview, people and employees of the company will post sample questions up there. It's pretty helpful.
How do you think it affected your approach to your senior year?
I think it got me out to a good start. I'm definitely thinking about employment opportunities now way ahead of time before I graduate. All being well, I'll be graduating in May, but I feel prepared now for the real world because unlike in school, where you're just doing one project after another, kind of rolling into one thing, when I was at least at Lamb Research, it was lots of meetings. It takes a long time. So this project that I was working on, my main one, helping with the transition, it's going to be a 2 or 3 year long project because there's so much that goes into it versus working on something in school where it's maybe 2 or 3 weeks. Just seeing that change, like how slow, I guess, things work in the real world and how many people you have to talk to get something approved is definitely gives me an advantage because I know how it's going to work now.
Questions? Thank you, Mckenzie.
Okay, so we're going to chat about the traveling salesman problem a little bit, and some of you might not have seen this before. I'm sure most of you have, but I'm going to give you a quick introduction to it, and I think for this, and we're also going to attack this with the emphasis on doing this on a phone, but for this problem, basically, I think the best way of seeing it is just a quick example. So first we're going to pretend that we just invented the new coolest, hottest iPhone case ever, or whatever phone. And it basically levitates when you drop it. So it's a pretty cool feature. Uses black magic, of course. So we've got to save the phones. And since we just invented this new cool thing, we've got to go hit all the vendors in town. We've got to hit all the Best Buys and everyone who potentially sells these things. So there's a bunch of people we want to go visit. And the first question we need to ask is who we're going to go to first. So we're curious. And here's an example graph, which we've all probably seen. Each node, so the A, B, C, D, E, can basically be thought of as one of the vendors that we could potentially visit. And basically we're going to try and figure out how many possible routes we could have here. So let's start with one easy one. We're going to go A, B, C, D, E, A. So that's just doing a loop, which we'll see right here. And that's going to be one possible path, but how many choices did we have that we didn't do? So let's talk about that mathematically. We started with 5 choices, and then there was 4 after we pick a starting point, and then there's 3, then there's 2, then there's 1. So this will seem like a factorial. There's a bit of overcounting going on here, which we'll talk about in a second. But just in general, 5 factorial. For those of you who haven't done factorials before, that's bad in CS. So this is basically run for the hills. So n factorial is a problem, and we're worried. And just as an example of how bad this can get, here's a quick thing that I found. If you imagine you have some computer, whatever specs it has, it can compute 1 million cycles, or it can find one of these cycles per, 1 million of them per second. So here's an example of that many nodes. So say 10, for example, you can finish in 1/3 of a second, it's fine. As we go down, 4 seconds, 40 seconds, 8 minutes, you'll see it just skyrockets at some point, and then you're going to hit 1 million years over here. So pretty quickly, this becomes just unbearably difficult to completely solve as like a brute force algorithm. Now, let's take a closer look at how we were overcounting, just to talk about the math. So basically, we picked a starting point, and then we went around in a loop. We went A, B, C, D, E. We could have gone A, C, E, D, all kinds of things. Every line between nodes is basically an edge, for those of you who haven't seen that. So let's take a look at that path. So we go through. And next up, let's ask the question of, let's check this path out. So this is basically that path, the original one, in reverse. And the question is, we're trying to look at what we've overcounted. So those 2 paths you can think of as the same, because you see obviously we're going just like that. It's going to be the same route. So we need to go ahead and exclude things like that. There's a bunch of them, and you'll see a lot of this as you go through CS and math potentially. So to counter this, basically we have 2 things that are happening. Each path we counted n times, and that's to say we could have started A, B, C, did it. We could have done B, C, did it all the way through. So we're going to divide by n to get rid of those. And then similar to what we've shown, we could have gone in both directions. So we're going to divide by 2. So long story short, that comes out to that complexity. And that'll get you all of the paths that we need to find, brute force. But of course, that's still a problem because it's factorial. So what we're going to do is we're going to use a decent estimate, and this is just the nearest first algorithm, or nearest neighbor. And this basically is what it sounds like. You're going to have a bunch of places. You grab the first one, and that's the closest. You're going to go there first, and then you're going to see how that estimate turns out. So here's a cool Wikipedia. This is just a GIF that I thought was pretty cool. So this first one is the brute force, and it's giving you a quick demo of 7 nodes, and it's showing you it has to go through and hit all of them. It takes a long time. And eventually, you'll see this one on the right is going to get updated, and that'll eventually have the optimal path. Down here is another algorithm, branch and bound. That's one's really good. Whoops. And then down here is nearest first. So you see how fast this completes. It'll be very quick. This is not going to get the exact optimal path in most cases. Sometimes it will. And you can see the distances will be slightly different. And that's this line right here. But it's a cool thing to check out if you're ever doing some of these later. Okay. So now we're going to talk about the application, and I'm going to give a few guidelines. So this was basically built under the premise of we're going to have a manager and some agents. So the manager, we're going to say, is the owner of some snack company. And basically he has a bunch of these vendors that he already knows, and he needs to complete these deliveries to those clients on a daily basis or when they request. And we're going to go to all of these clients. He's starting out with 30 or more, so that's a big number, obviously, with the factorial. But we'll see with the nearest first, that's not going to be an issue. And now he wants to have an optimized route for all of his agents. So it's a manager, he has a bunch of agents, they go do the deliveries, he manages all the agents. And we'll take a quick look at the agents. They're doing the deliveries, and they also need to provide location updates as they do their deliveries. This is similar to your Amazon, your UPS, etc., where you can say, oh, they're almost here. I got my new iPhone. And then the primary goal as far as me doing this semester was to mess with Swift and iOS and all the entire Apple ecosystem because I hadn't used it that much. So I have this running on my phone, but unfortunately my hard drive kicked out on me this morning, so I had to record a video of me showing this. But this is basically the manager's app, and what will happen is he's going to pull this up, it's going to go to the server and grab, and this is all iCloud, it's going to grab all the agents, so that's like a list of a few agents. So as soon as we open that up, we can see everyone. We're going to go down here in the bottom right, and that's basically that's all of the clients. So that would be all of the gas stations or vendors in this point. And it's going to use the nearest first and find an optimal route to visit all of these. Now, one other concession we're making here that's useful for us is that we have multiple agents. So we can actually split this up, which will get us a bit better. It's a bit easier to get the route. And you'll see that that's a little sparse. So now we go back to the agents tab here. And this is basically, you can see, I picked one person. So this is Tom Brady. Well, that's fun. And so Tom Brady starts work, and he's going to see on his map that, oh, I need to hit these locations today. That's the red pins. You can click on any of the pins, and it'll show you the place. That's the address of the first one. You'll see he went to the first place, and then he kind of died off. So the green line was where he's been, and that'll obviously overlap as he completes his route. So let's check out this Ryan guy and see what he's been up to. So he started off, and looks like he hit a few of them, and then he decided to go somewhere. It looks like he went to the casino. So you can't trust that guy. And he missed one. So that's bad, Ryan. We're going to check out Adrian Peterson. He's pretty reliable. So let's see what he's been up to. Again, green line overlaps. He actually did his job. So we got one good agent. And you can see the whole map. You see his route. And I think I'm going to show directions here. And then I'll show you the next app real quick. Okay, let me jump forward. So just real quick, the agents apps basically, they have the same routes that'll display for them automatically, and then they can click the link to get directions to each place. So they can see their route and just go hit, and then they're done. So the manager kind of showed everything, and then the agents they have those routes already pre-computed when they log in. So, yeah.
Thank you so much, Ryan. Questions for Ryan?
Oh, yeah.
Did you mention where you worked?
Work? No.
Where did you work over summer or when?
I didn't. This was just independent.
Oh,
Yeah.
okay, gotcha.
Yeah. Just wanted to mess with Swift and everything.
Sure.
And this whole thing was done in like Swift 2.0/2.1, so it's very new.
What was your experience with Swift? Did you like it?
I loved
Ups and
it.
downs?
I mean, the greatest parallel is really Python, but it just kills Python on performance from what I've seen so far. But I mean, it's so similar. So yeah. In the back.
So you,
Either of you.
so you said that you calculated like the routes using that nearest first.
Yeah.
Did you also use the built-in thing like the Apple Maps so that you're not like.
Yeah. So everything in there is all Apple APIs. I tried to steer away from Google for now, just because I wanted to really hit Apple and see what they have to offer. So yeah, all the directions are using the maps locations and everything built into iOS. So yeah.
Do you have experience with Objective-C?
Yeah, there's some Objective-C in there just because it's so robust. But I mean, if you see the two side by side, the Swift just kills it. It's crazy. Yeah.
So, I'm just curious what that data set is. How did you get that data?
So the whole thing's stored on a CloudKit database, and that's similar to SQL, if you've probably done that, right? Yeah, so I mean, it's basically exactly what you've seen in MySQL.
No, I mean, like, is that stores that you were just entering when you're making the project?
Oh, I grabbed gas stations, local gas stations, and then all the routes were me driving around. So the joke I made with Tom Brady was actually I ran out of gas, so I was like, I'm probably done for the night. I'll stop. Anyone else? Okay.
Thank you, Ryan.
So my name's Marty, and I worked with Dr. Revor this semester on a project that actually started when I was at Lawrence Livermore National Labs, which is something I'll talk about after this discussion, I guess. So what this was a study to determine how to do efficient model-specific register access, and I'll explain what those are in just a second. So model-specific register, it's something that was introduced by Intel several years ago with their 8386 processor. Back then they had I think it was 4 or 6 registers. It was some super small set of registers that you could go and poke at and look at some various information about the processor. Now these registers have kind of taken off, and they're available on most modern processor architectures, although the one I'm going to be talking about today is Intel specifically. They're used for things like debugging, program execution tracing. You can actually go to one register and write an address of an instruction, and then go to another register and say, go and jump to that address in so many nanoseconds. And then all of a sudden something will wind up getting called. There's also lots of different counters that are available in there that you have access to track different things. Performance monitoring, you can watch how many cache hits you've had, you can look at memory access, lots of different timing things. You can enable and disable different CPU features. You can turn on hyperthreading, you can turn it off. Pretty much everything that you can do in the BIOS is also available through these MSRs, and you can touch them. This actually plays into one of the problems, because you can do some very bad things with MSRs and really hurt computers, as I'll show. Another thing you can do is set power limits. This is really all of these are actually really important for supercomputing. When somebody's running an experiment, it costs a significant amount of money to run a machine that has 1 million cores. And I've seen a machine that has 1 million cores. So there's a lot of monitoring that goes on, a lot of things that go on to make sure, are we effectively utilizing all these cores? If we're not utilizing them, are we ratcheting the power appropriately? I think there's a wiki page that I looked up just before this discussion. There's another lab that has a really large supercomputer, And they're estimating that if it were to run at full power, it would be about a $4 to $5 million budget just for the power bill. So, you know, a lot of these computers, they take up a serious amount of energy. Modern CPUs now come, you know, with hundreds of MSRs. It's incredible. I had no idea when I was asked last year if I'd ever heard of an MSR, and I said no, and he said, oh, well, you'll learn about them. The Intel manual has hundreds of pages describing different MSRs and different accesses you can do to them. So MSR, it's a simple instruction. It literally is. That's the instruction. It's read MSR, take that operand on the right is the number, the MSR number, you know, 1 through 200 or something like that, and store it in a register. That's all there is to it. You know, so what's the big deal? Why is this such a problem? Well, the first thing that's problematic is it's privilege level 0. What this means is unless you're running DOS or some standalone operating system, you can't call it from user space. If you write a program, even with Professor Lyle's help, and you write an assembly language instruction to do that, your program's going to core dump. It's just going to, it won't let you execute that instruction. There's reasons for it being privilege level. Some of the dangerous things you can do, you can literally turn the machine off, just bam, with one of the MSR accesses. So it needs to be done inside the operating system. The other thing that's kind of complicated is these registers, they're associated with each core in a machine. So, you know, you got a desktop at home, it's got 4 cores on it, or, you know, 8. This instruction has to be run on the machine for which you want to get that MSR. So you can't, you know, if you're an application, you're running on processor 0, and you want to find out the contents of an MSR on processor 4, somehow that instruction has to be actually executed by processor number 4. So one of the things I wanted to do was kind of walk you through how MSR access is actually done. And this is with a fairly recent version of Linux, the Linux operating system. This is what has to happen when you actually read, let's say I want to go out and find out you know, some current counter in the system, and I want to read one of these MSRs. You'd have an application up in user space. It has to make the standard system call to get to the kernel module. It has to do an open of this kernel module. Then it has to do a system call, either a read or an IOCTL or something like that, to start the action. The kernel module will then take that system call, and it will copy in all of the parameters for what you're trying to do. It'll validate and make sure that it looks good and that it's not going to crash the kernel. Then it calls a function that's inside the kernel, a multiprocessor function that will, the first thing it does is it actually sets up a callback inside the kernel. And that callback actually contains this code that's got this instruction in it. And what it's going to, it's a callback that'll get called by an interrupt, and I'll show you what happens next. So the next thing, after it's registered this callback, the next thing that it does is it calls a CPU instantiation mechanism. What this does is it actually tickles a piece of hardware, and that hardware then is going to generate an interrupt, a hardware interrupt, to the particular processor that you're wanting to go to. After it sends this signal to the hardware device, it then goes over into a synchronization object and goes to sleep. It says, I'm just going to wait until somebody later on tells me that the operation that I've enqueued gets done. The next thing that happens is the hardware actually does generate the interrupt, and it winds up going to the interrupt service routine for the interprocessor interrupt handler. That interrupt handler looks at its data structures and says, oh, I've got a callback that needs to be called, and winds up making a call back to the callback that was previously registered. And voila, that read MSR instruction gets executed. Once the execution gets done, the MSR callback then will signal number 8, it'll send a signal to the synchronization object saying, hey, I'm done with this particular operation. And at that point in time, the multiprocessor function, who's sitting here waiting, wakes up, says, great, I got my stuff. And the multiprocessor function winds up returning back to the kernel module, and the kernel module takes the stuff that the MSR contents, it copies that stuff from kernel space out to user space, and finally returns to the user application. User application has no idea that all this stuff went on, and this is just for one instruction that needs to occur. So this mechanism, you might think, well, it's not so bad. You don't read MSRs that often. The issue is that in supercomputing especially, you're wanting to actually access a large set of MSRs rather often, sometimes on the millisecond range or frequency. And doing this one at a time is quite problematic. And some of the work that was done this summer was it used this exact same framework, but instead of doing one operation at a time, it allowed for the application to say, do 10 or do 15 different read MSRs, and it would just sit there in a loop and do them. This works just fine. There's a slight problem with it, or a drawback to it, and that's because since that MSR callback is being called from an interrupt service routine, I don't know how many of you have taken operating systems yet, but preemption has to be disabled. So during the time that thing's running and executing these read MSR instructions, nothing else can preempt that running. It has to have total access to the CPU, and it's going to just keep it until it gets done. So one of the ideas, and this is the research that I did this semester, was what if we replaced this callback mechanism with a worker thread? The Linux kernel actually allows you to create and manage kernel threads that actually live in kernel space. They aren't managed by user space applications. They just live up there. What if we had a kernel module that when it got loaded the very first time into the kernel, it created a separate kernel thread per processor? And now when an MSR request comes in, what happens is it winds up putting it onto a work queue. And this work queue, the worker thread, is also waiting on that work queue for things to do. So when something gets put on the work queue, the worker thread becomes runnable. And when it becomes runnable, and this is another subtle point that becomes a little important later, when it becomes runnable, it doesn't run right away. It runs when the scheduler says it should run. And the scheduler says it should run when it gets a schedulable event. Schedulable events are things like I/O completions. Most predominantly, they are the clock. If you think about the clock that's just going off at a regular time interval, one of the things that clock does is it checks in with the scheduler and has the scheduler check to see if there's anything to run, if it's got anything on the run queue. So there's a potential drawback with this, and we'll discuss that a little bit. But the good news is, that's a thread. It acts just like any other threads. It can be preempted. It can be, other things can come in and run if they need to. It's not going to hog the CPU. So for this study, what I wound up doing was implementing a kernel thread prototype, which just discussed. I instrumented both, since it's Linux, we get the source. I instrumented both the kernel module that was there, as well as the thread-based one, so that I could take some timings. Wrote a little application and started doing some comparisons of timings. What I saw was, comparing the two different implementations. For the operation itself, it took negligible time, just a few nanoseconds to actually complete the instruction. The system call overhead itself, just doing that setup and everything, that also was fairly similar. The interrupt, though, the interrupt on the actual the scheduling part and the actual doing the instructions took a significantly less amount of time with the interrupt service function than it did with the thread. And what's worse is, if you look at standard deviation, is the interrupt, the deviation was very low. It pretty much took those things almost exactly when it was told to do it all the time. With the thread, it was all over the place. I believe that the reason it was all over the place is back to the schedulable event thing. You know, you give it something to do, and depending on when you gave it something to do and when the next clock tick is going to come in, that's going to vary. And you actually see it in this. So, to wrap up, I think that even though there's high deviation, there's still argument for more kernel thread work that needs to get done. I think that the interrupt callbacks are good, and they may be necessary for a very small subset of MSRs, but perhaps the rest can be done at a thread level. One option is you could actually create these threads and have them be programmed to or configured to go and read these MSRs at a regular frequency and just update a memory location. And then if that memory location was shared with user space, all the user space applications would have to do is read a memory location instead of having to make a system call, bypassing all of those other steps. That's what I did this fall.
I feel like the showstopper in chief. Questions for Marty?
What hardware were you doing this on?
This was on an Ivy Bridge. It was on one of my machines at home.
So on your model, you had one worker thread waiting for a schedulable event. One thing I noticed in a few languages is you can have a thread pool manager or just a queue of threads waiting to be used.
Mm-hmm.
I'm not sure if there's more overhead in time that make it slower than this one thread model, but would that be something to handle, say, multiple
You certainly need to have multiple threads when you have to have at least one thread per CPU. But doing multiple threads on the same CPU, they're kind of gonna only one can run at a time since it's just one CPU that's doing the work.
Questions? Thank you, Marty.
There's one more. One more.
One more.
Are there steps that you think you could take to improve the behavior of the scheduler, such that the standard deviation is minimized?
I don't know. Certainly some research could go into that. I'm not sure. I don't know if one of the things I didn't play with was messing around with the priority of the kernel thread, and perhaps giving it higher priority would somehow put it on something. But if you think about it, there aren't too many things that cause the scheduler to go, and the clock seems to be the primary source. So unless we can find some other way, I'm not sure. We could do an interprocessor interrupt. Actually, yeah, so we could do a hybrid of what we had before. We do an interprocessor interrupt, and what the callback function does is all it does is it causes the scheduler to run. So yes, I guess that would be an option. That's a good idea, actually. Okay.
Thank you. Marty stays.
Oh,
Marty
okay.
Yes, indeed. So, it's my pleasure to introduce Marty to Battlefield 2.0.
Yeah.
Marty is going to talk about his internship experience this past summer at Lawrence Livermore National Lab.
Yeah, so last year while I was in Dr. Revor's architecture class, one of the folks from the lab, from Lawrence Livermore Lab, came and talked at the colloquium here. And because Dr. Revor knew that I was interested in architecture and knew a couple of other students in the class were interested in architecture, Mallory and Scott, she sent us an email saying, "Are you guys interested in this? And if you are, send a resume." And all of us did. And all of us wound up getting to participate in a summer-long program where they had several hundred interns show up there. Lawrence Livermore National Labs is a 1-by-1 square mile facility. It's huge. It's like a little mini city. It Takes a little getting used to. It's guarded by armed guards. They do a lot of different studies inside of Lawrence Livermore Labs. Some of it is top secret and you don't have access to. But others are studying weather patterns, doing physics experiments, doing biological experiments that wind up needing to use huge, significant amounts of CPU resources that they have command of there. And Scott and Mallory and I went to work for the computation staff there. And what the computation staff does is they basically support an entire infrastructure of postdocs and grad students that are running experiments. And what I mean by support is we get to actually play around and write operating system code. We get to write libraries in C and C++ that will allow higher level debugging and profiling tools, access to these MSRs and things like that. And they use those to help model how their software is going to be run. And once they get it down to where they think, yeah, this works on 10,000 nodes pretty well, we're getting ready, we can now do our 1,000,000 node test. It's a big deal. They run these tests and they reserve the system out for this long period of time, and if the thing crashes, nobody loses their job, but it's a big deal. It's hard to actually get the funding and the budgeting for running these experiments because they do cost money to run. So what we did, us and a bunch of other students, the students were from all sorts of other areas besides computer science. The representation from here at SSU is computer science, but they had chemistry, biology, physics students, all working different aspects over there. What I got to work on specifically was that model that I showed you. The kernel that exists today, it only does one MSR instruction. And the one that we've got now that Red Hat is currently testing will allow you to do however many MSRs you want in the context of that. And this saved a pretty significant chunk of efficiency. And a highlight for me is the stuff just got through Red Hat, and I got called from the guy that I was working with this summer, and they're wanting to get it into the mainstream Linux. So I'm working through some of the process of getting some modifications to the MSR subsystem that I was able to have a hand in. That was fun. It's a neat thing to go back to. Another thing that they do towards the end of the cycle is they have kind of a job fair day where they kind of collect all the students that were there, all the interns that were there, and find out what they liked about the program, what they didn't like about the program, whether they were interested in becoming PhD students, whether they were interested in stopping and starting to work and do something, and if they are, would they potentially be interested in, is there some fit within Lawrence Livermore National Labs? That was a good thing. They found out, quite a bit. I think that they helped. Can I speak for Scott? I know that they helped Scott and Mallory because they wound up signing them up for follow-on work after the program. They also wound up signing me on for follow-on work, and the thing I'm really excited about is they signed me up for a full-time job on January 4th. So I'm effective as soon as I can get done with all this stuff that you say is easy and we don't have to worry about. As soon as I get done with that, I'll get to go and play with some big toys. Any questions? Oh, I highly recommend, tell your professor if you're interested in a class, if you're in some class, and you're going to find different things. Some classes you're not going to be as interested in as others. But if you find a class or a set of classes that you're interested in, let your professor know, because you just never know. Some of these colloquiums come around. The professors know people, and it's possible that an internship could become available for you. And I highly recommend it. It's an excellent experience, and it does, like Mckenzie was saying, it exposes you to some more real world aspects and some of the problems they have to face, so you don't quite get hit with it on your first day out of school. Somebody raised their hand. Yeah.
What was the interview process like?
So I sent in my resume, and then I got an email, and then I wound up talking to the person that was my mentor on the phone. So it was a phone interview that lasted about 40 minutes. It wasn't a classic interview. It was more, what kinds of things are you interested in? What types of things in school are you most thrilled to work on? What types of things, would you like to work on when you came here? Here's some things that we do. What would you be interested in? And they have a big, they have a big net of people that they bring in. So in a way, they aren't trying to get down to the nitty-gritty details of everybody. They're just wanting to bring them into the program, see how they work, see how it goes.
Thank you very much.